Hey there and welcome. So, you've seen the periodic table, right? It's the absolute foundation of chemistry. But let's be real for a second. Its shape is just bizarre. It's not a nice, neat grid. You've got these tall towers, these wide valleys, and that weird little island of elements floating down at the bottom. Well, today, we're going to crack the code and find out why it's built that way.
Okay, so let's just ask the question right out of the gate. What is the deal with this shape? I can promise you it is not random. The answer isn't really about the elements themselves. Nope, the secret is hidden deep inside their atoms. It's all about where the electrons live. And trust me, it's a way stranger and cooler story than you might think.
Now, you probably remember this picture from science class, the good old Bohr model. It's so clean, so simple. You got the nucleus in the center, and you've got these electrons just zipping around in perfect little circles, kind of like planets orbiting the sun. It was a fantastic idea for its time, but it's an outdated map. And to understand the periodic table, we need a much better one.
You see, that's what science is all about, right? You're constantly updating your maps as you discover new things. And back in the early 20th century, some game-changing ideas, like electrons acting as waves and the Heisenberg uncertainty principle, showed that the simple little Bohr model just wasn't the whole story. It was time to dive into a deeper and, honestly, a much weirder reality.
And this, right here, is the quantum leap. It's a huge shift in thinking. We left behind the certainty of the Bohr model, where you could say the electron is right here, and we jumped into the uncertainty of the quantum model. In this new picture, an electron isn't just a tiny ball. It acts like both a particle and a wave. You can't actually know its exact position and speed at the same time. All you can talk about are these fuzzy regions of probability, these clouds where the electron is most likely to be found.
So that means we have to throw out the old idea of an orbit. Instead, we get a new concept, and this is the key to everything, the orbital. An orbital is not a path. It's a 3D shape, a probability cloud. You can think of it as the electron's home base, the zone where it spends most of its time. This idea is the fundamental building block we need.
Okay, so if orbitals are an electron's home, how do we know which electron lives where? Well, luckily for us, quantum mechanics gives us this incredible atomic address system. It's a set of rules that perfectly describes how electrons organize themselves inside an atom. And get this address system is the direct blueprint for the periodic table.
By far the easiest way to wrap your head around this is to imagine an electron apartment building. It's a great analogy. The main energy levels, which we call shells, are the floors of the building. On each floor, you've got different types of apartments, and those are the subshells. Each apartment is made up of rooms. Those are the orbitals. And finally, every room can hold a maximum of 2 tenants, and those are our electrons. So, the first part of the address is the shell, which we call N. This is just the main energy level. Think of it as the floor number. Floor 1 is closest to the nucleus, the ground floor, so it has the lowest energy. Floor 2 is a little higher up, a bit more energy. Floor 3, even more, and so on. Simple enough. But, each floor isn't just one giant empty space. It's divided into subshells, which are like different apartment layouts. We give them letters: S, P, D, and F. An S subshell is like a basic studio apartment. Very simple. But the P, D, and F apartments get progressively bigger and have much more complex layouts.
And here's the deal. Each of these apartment types has a very specific capacity. The S apartment, or studio, has just 1 room, so it can hold 2 electrons. A P apartment has 3 rooms, so it holds up to 6. A D has 5 rooms for 10 electrons, and the big F apartment has 7 rooms for 14. This fixed structure is absolutely crucial for what's coming next.
Okay, so we've got our building, we know about the floors, the apartment types, the rooms, but how do our electron tenants actually move in? Well, they don't just pick a room at random, oh no. There are very strict rules they have to follow, and it's all governed by one thing: energy.
This right here is the #1 rule. You could call it the landlord's decree. Electrons are, well, kind of lazy. They always fill the lowest energy spot that's available first. They start on the ground floor and they work their way up, always taking the easiest path. So what this really means is we have to know the exact energy order of all those apartments.
And yeah, that's the $1,000,000 question, isn't it? Because it's not as simple as just going floor by floor, 1, then 2, then 3. Things get weird. Sometimes an apartment on a higher floor can actually have less energy than one on the floor below it. So how on earth do we figure out that order? Well, lucky for us, there's a beautifully simple trick. It's a master key called the N plus L rule.
All you do is take the shell number, n, that's our floor number, and add it to a number for the subshell, L. It's easy. For S, L is 0. For P, it's 1, D is 2, and F is 3. Whichever subshell has the lowest n plus L value, that's the one with the lowest energy. That's it. That's the key.
Let's put this rule to the test. This is the classic example that blows people's minds. You've got the 3D subshell on the 3rd floor and the 4s subshell on the 4th floor. Common sense says 3D comes first, right? Well, let's do the math. For 3D, n is 3 and L is 2, so 3 plus 2 is 5. For 4s, n is 4 and L is 0, so 4 plus 0 is 4. 4 is less than 5, which means the 4s subshell on the 4th floor actually has lower energy and fills up before the 3D. This one surprising overlap is the real secret to the table's shape.
And just like that, we have everything we need. We know the structure of the atom's apartment building, and we know the rules for how electrons move in. With this knowledge, we can finally decode the periodic table and see it for what it truly is, a perfect visual map of this electron-filling order.
So let's just pick one. How about scandium? It has 21 electrons, so we start filling up our apartments according to the rules, lowest energy first. You can see the order here. 1s, 2s, 2p, 3s, 3p, and then boom, the 4s gets its 2 electrons before that very last electron goes into the 3d. This whole long string of letters and numbers, we call that the electron configuration.
Now watch this. This is where the magic happens. That configuration isn't just a list, it's a set of coordinates. The highest shell number, the highest n value, is 4. That tells us scandium is in period 4, the 4th row. The subshell of the very last electron we added was D. That tells us it's in the D block. And for elements in the D block, if you add up the electrons in the outermost S and D subshells, so 2 plus 1, you get 3. That's the group number. Period 4, group 3. Go look it up. That is exactly where you'll find scandium. And the amazing thing is, this works for every single element. That weird, clunky shape of the periodic table is actually a perfect map of the S, P, D, and F blocks, all laid out according to the quantum mechanical rules of energy. It is a beautiful, logical system that was just hiding in plain sight. The mystery of the shape is officially solved. But just when you think you've got it all figured out, nature throws in one last, fascinating little twist. What happens when following the rules to the letter isn't actually the most stable way to do things? Well, sometimes the system breaks its own rules to find an even more stable, even more elegant solution. Take a look at chromium and copper. Based on all our rules, we'd expect their electron configurations to look like the ones on the left. But that's not what we actually see in nature. What really happens is that one of the electrons from the 4s subshell actually jumps up to the 3d subshell. Now, why on earth would it do that? It's moving to a higher energy level. It all comes down to symmetry. It turns out that there's a special kind of stability that comes with a subshell being exactly half full, like D5, or completely full, like D10. Nature prefers this symmetrical arrangement so much that it's worth the small energy cost to promote one electron to achieve it. So it's not really breaking the rules. It's just following a deeper rule, a rule of stability. So there you have it. The periodic table's shape is a direct consequence of the quantum address of every atom's electrons. And that code doesn't just give an element its location on a chart. It gives it its identity, its very properties. Which leaves us with one last really big question to think about. If an element is defined by this code, what happens when we figure out how to rewrite it?